All right, it's time for an example with frame elements for finite elements analysis. Here we're going to take a look at an example where we have a box frame here and we have supporting truss elements on the interior with a triangle distributed load on either side. All right, let's go ahead and get started. The problem statement, there it is again, same problem. 4 truss elements on the inside, frame elements on the outside, and we want to find the usual suspects: displacements, reactions, and elemental loads. So the solution process, well, this should look familiar by now. We'll go ahead and figure out what our elemental stiffness matrices look like, assemble those into the global stiffness matrix, and then reduce the global stiffness matrix by applying constraints. And then once we have that reduced matrix, we can apply some loads and then end up solving for our displacements. Once we have those displacements, we go ahead and plug those back into the global stiffness matrix to solve for our reactions. And then we can go ahead and use these same displacements, throw them back into the elemental stiffness matrices to solve for our elemental loads. You'll notice I left a gap here, and that gap is because with this problem we have one preliminary step, step 0, which is how can we create an equivalent symmetric model? Why do we need to do that? Let's go ahead and take a look at us doing that, and in the process we'll describe why we need to do this. So this is our equivalent model using symmetry. We'll go ahead and draw the same model that we had before. Notice that there are not any constraints anywhere to be found on this whole model. That's a big no-no in finite elements analysis. It would not be able to invert the matrix when trying to solve for displacements, and so you would just get a bunch of warnings, or probably a bunch of errors saying that you got infinite displacements. So what we're going to do before we set up the symmetrical model is go ahead and create what we think the displacements will look like. And when we look at what these displacements look like, we see that there's going to be symmetry about 2 planes. If that's the case, we're just going to go ahead and highlight the section of the model in that upper right quadrant, and we'll use that to create our model for FEA. All right, now notice when we have this model, we have a roller constraint here on the left side, which corresponds to what would be right here. We have that roller constraint, so it is allowed to move up and down vertically, not horizontally. Notice that it also does not have a pinned constraint. There is a pin joint at this node between this element and this element, but there is not a pin constraint, and that's because we want to make sure that that angle maintains a continuous 0 degrees, and so that's what this type of constraint does there. And you'll notice a very similar type constraint over at node 3. Okay, so first thing we'll do is go ahead and set up some elemental stiffness matrix equations, and go ahead and take a look at our model that we drew on the previous slide. And we'll set up a table that sort of helps organize things when we start creating these elemental stiffness matrix equations. So we're taking a look at element 1 first. That's our truss element going from node 1 to node 3. Note that the angle we have is minus phi1. This is phi1. First of all, we made sure to measure this angle from node 1. First node defined, right? Not necessarily that it is node 1, but it is the first node defined. That's why we're measuring it from here, and we measure it from the horizontal axis every time. And because this makes a clockwise rotation from that horizontal axis at node 1, or the first node defined, that's why we have a negative sign there. If it was counterclockwise, then there would not be a negative sign. All right, here we have our corresponding degrees of freedom, 1, 2, 3. That corresponds to the translations and rotation at node 1. 7, 8, 9 corresponds to the translations and rotation at node 3. Pretty usual inputs here: elastic modulus, cross-sectional area, no area of moment of inertia, and that's because this is a truss element. If it's a truss element, there is no bending stiffness, so we take that out by putting in a 0 there, and we have a length L1, just be Pythagorean theorem, right? Square root of this length squared plus this length squared, not scared, squared. But for simplicity, we'll go ahead and use just this length. Okay. Element 2, define it from nodes 1 to 2, 0 degrees because it's perfectly horizontal, going in the same direction. If I did define it as node 2 to 1, then it would be minus 180 degrees or 180 degrees because it would end up going in this direction. All right, degrees of freedom correspond to these nodes. Here are some inputs we have. We do have an area moment of inertia now since this is the frame element. And for element 3, we'll notice that we have the same cross-sectional area and same area moment of inertia. Note that node 3 is defined first here instead of node 2. And does it need to be? It doesn't matter which order as long as we're consistent. And since that's the order that we chose, we are measuring this angle from node 3 up to node 2. So it's making it from the plus x-axis all the way up there. That's why we have 90 degrees. Notice that we also put the degrees of freedom corresponding to node 3 first before the degrees of freedom corresponding to node 2. And yeah, these inputs are all the same as for element 2, except we have a different length. Still working with elemental stiffness matrices. First, in the elemental coordinate system, here is our baseline equation for a frame element in its elemental coordinate system. But first we're going to review the truss element. So we have nodes 1 to 3. We go ahead and change those in the subscripts. Area A1. And since the area moment of inertia is 0, make a lot of substitutions there, changing it all to 0. And just some more subscripts for length equals L1. Great. This is our nomenclature or the way we would write this equation for the elemental stiffness matrix in the elemental coordinate system for truss element 1. All right, we're going ahead and continuing for now, which is the first frame element 2. Nodes 1 to 2, we'll go ahead and make some substitutions there. Area A2, some subscripts. We'll just keep that the same. Length equals L2, we'll go ahead and add some more subscripts. And we're done. This is the way we go ahead and write this equation, the elemental stiffness matrix equation for element 2 in the elemental coordinate system. The last one, frame element number 3, third element, second frame element, nodes 3 to 2. Notice that node 3 subscript comes before node 2, trying to make sure that we're consistent. Same area as frame element 2, so go ahead and have that. Just leaving that area moment of inertia in there and then changing the subscripts for all the lengths to be length 3. And this is how we would write the equation for the stiffness matrix for element 3 in its elemental coordinate system. That's what these apostrophes are there for. All right. Still on the first step, the longest step in this type of problem, where we transform. Now we're transforming the elemental stiffness matrix equations into the global coordinates because, well, they all have to have the same coordinate system in order to add them up. And as the note implies, this is going to be just like transforming truss elements. We're drawing just a general arbitrary frame element up there. And here we have some loads in the elemental coordinate system. Here's the angle of the element. And we'll go ahead and write our transformation matrix according to that angle, that arbitrary angle drawn right there. And these would be our forces and moments in the global coordinates, drawing those in yellow. Now this is exactly the same as what we've seen for our truss element equations, but notice that in the truss elements we didn't bother with the moments, and here we are. And notice that we just go ahead and throw a 1 in there. That means that there is no transformation. This is a 2D problem, so these rotations are occurring about the same axis that's coming out of the page. Alright, so that's our transformation matrix. We have a transformation matrix for each element. We'll go ahead and draw the general form of it. So element K, and then we'll go ahead and write a table with our element numbers, the corresponding angles of rotation that we would go ahead and put in there. And these all correspond to the diagram that we had earlier. And then just for reference, we have the node order for each of those elements. All right, still on step 1. My goodness. But now we're finally going to go take these elemental stiffness matrix equations and put them into the global coordinate system. So first thing we'll do is we'll write just the general transformation matrix equation going from our loads in the global coordinate system to our loads in the elemental coordinate system. And we can use that same transformation matrix we have here to transform our displacements from the global coordinate system to the elemental coordinate system. We'll write our elemental stiffness matrix equation, has the apostrophes there, so this is in the elemental coordinate system. We'll go ahead and make some substitutions there for the force vector and then also for the displacement vector. And if we go ahead and introduce those substitutions, we get the following. Go ahead and bring that transformation matrix that we have here over to here. And noting that due to the principle of orthogonality, that inverse can turn into a transpose. And with that, we have an equation for our elemental stiffness matrices in the global coordinate system. Great, finally we're on step 2. How about that? This is one we should all be familiar with now. Combine our elemental stiffness matrices into the global coordinate system, drawing our diagram again for reference, writing out the empty global stiffness matrix equation. Then we're just going to go ahead and populate it by each element. So looking at element 1, connecting nodes 1 and 3 with these degrees of freedom, we just go ahead and match up those degrees of freedom and plug those values from the elemental stiffness matrix. It's a 6x6, and we just plug it in these locations here that correspond to these degrees of freedom. And we do the exact same thing for element 2, and we also do the exact same thing for element 3. Now note in element 3 that we're going from node 3 to node 2, so we'd actually take that upper left quadrant from the stiffness matrix of element 3 and we'd actually throw it. Oh, let's see. There you are. We would throw it down here, and then we take the bottom right segment, throw it up here. Does it sound confusing? It is confusing. That's why you just have MATLAB do it, or whatever software you want to do it. Just being consistent with how you write it, it will take care of it for you. All right. Now we're going to go ahead and reduce that global stiffness matrix by applying our constraints. There's our model again. There's our global stiffness matrix copied from the previous slide. And so we'll go ahead and take a look at our first constraint, knowing that node 1 is not allowed to translate in the x direction, so we'll just go ahead and remove the row and column corresponding to that. Similarly, not allowed to rotate, remove the row and column corresponding to that. Looking at node 3, it cannot move vertically, removing some more rows and columns. And finally, not allowed to rotate at node 3, so we'll go ahead and remove that. And if we go ahead and remove all those items, we end up getting the following reduced stiffness matrix equation. Starting to get complex now. I wanted this whole example just to be symbolic, so if you can just trust me that we remove those, this would be our reduced stiffness matrix there in the middle. Oh, there we go. And this would be our reduced displacement vector, and this would be our reduced force vector. All right, so now we're moving on to step 4, which is where we're apply loads and we solve for our displacements. But the first thing we need to do is take that distributed load that we have here and transform that into work equivalent nodal forces and moments. Now, I don't have it here, but you would just reference a table and to be able to do that. Or there was a previous video where you could actually go through the motions of those equations utilizing the shape functions for frame elements in order to figure out what the equivalent loads would be. But we're going to assume that you can just look this up. It's a pretty common type of load, that triangle load. And so if you went ahead and did that, you would get the following force and moment at the bottom node where the bigger part of the triangle load is. You can get the following for the top node where the triangle drops down to 0. And then we just go ahead and substitute that. We'll say, well, this will be the load for the horizontal force at node 2. This would be the horizontal force at node 3. That would be our moment applied to node 2. And that would be our moment applied to node 3. Note that I included a negative sign here just because, well, since this is going clockwise, as we would enter it into the reduced stiffness matrix equation, it would be that. But it turns out we don't need to worry about that because this degree of freedom is constrained anyway. But good to know just good to know in general, I suppose. So now we're going to go ahead and apply our loads, solve for the displacements. That's our reduced stiffness matrix equation that we had from the previous slide. We're just going to go ahead and replace those forces with values that we had from our work equivalent loads. And so we'll go ahead and write the equation that we have here in this matrix notation. And we'll go ahead and invert that reduced stiffness matrix to figure out what our displacements are. And this inversion here, when you're going ahead and use a commercial software with a lot of nodes, a lot of elements, that's what's taken all the time. Okay. So now we can use those displacements. Let's go ahead and assume that those are all known now. We can use those to solve for our reactions. So drawing our diagram again, writing out our global stiffness matrix equation. You'll note that we already made some substitutions, it looks like. Took all those constrained degrees of freedom and changed those to 0. And these other values we now know because we solved for it in the previous step. So since that's all known, we just go ahead and do straight matrix multiplication. And if we do that, we would get a lot of values for this, but those values actually correspond to applied loads and reactions. And so to actually solve our reactions, we would need to subtract the applied loads. But we want to be careful because since we do have distributed loading here, that means we had work equivalent loads being applied. And so especially for our moment at 3, there would be, part of it would be a component in the reaction, but part of it would also be an applied load. So we'd have to be very careful to take this step to figure out what the correct reaction moment is at node 3. All right, last step, solving for the elemental results in the elemental coordinate system. Most specifically, the elemental forces and moments. This is our general equation, right? This would be our elemental stiffness matrix equation in the global coordinates, written as is, but we go ahead and apply that transformation matrix, which gives us our loads in the elemental coordinate system, which is where we want, probably where we want them. All right, so that's all the values we would get. We would get forces in the x and y directions and a moment at each node. So here's an example of this arbitrary frame element being drawn there. Now, while we could do that and the multiplication is simple enough, we want to make sure that we convert those values to what the appropriate elemental sign is. So all those values that we would get from that matrix multiplication on the previous slide, those are positive nodal directions. But as we report them, we want to know, well, what do they correspond to in terms of the element? What's the element experiencing? So if the element's experiencing tension, it would look like this. If it's experiencing what we call positive shear, it would look like that. And if it's experiencing positive bending, it would look like that. And so now we just take a look at each of these values on the left side and on the right side, and we just go ahead and compare them to what the default positive nodal directions are on both sides. And when we do that, we see that, well, the force at node 1 in the axial direction, well, that's opposite to what is considered positive for tension in the element. This would be the same. And we go ahead and do that for our shear, right? This is the same direction as what's considered positive shear. That's the opposite. Lastly, do it for our moment. That's the opposite direction as what's considered positive bending on the left side, and it's the same on the right side. All right, so here's some example results. Doesn't necessarily mean that this what would correspond to this problem. We didn't even give values for this problem, but we just want to see how we would interpret some sample results. So we'll start off with some x values. Now I noticed just now that we should probably put little marks right here to indicate that this is the elemental coordinate system. You never notice it until you're doing a live video of it. All right, so now we'll go ahead and take a look at this value and this value. We'll go ahead and interpret that to what's happening with the axial loading. I select this value at the bottom because that corresponds to the same direction, that nodal direction is the same direction as what's considered positive tension. Similarly, for our shear, I select the top one, because that top one corresponds with the same direction as what's considered positive shear. And finally, we have our moment values. And so we go ahead and take a look at that top one. Notice that I flipped the sign, and I flipped the sign because on the left end, this moment is going in the opposite direction. Pardon me, I should say the positive nodal direction is the opposite of what's considered positive for bending. And so that's why we flipped the sign there. And then this is the same direction for the nodal direction as what's considered positive for bending. So we'll go ahead and keep that sign the same. And then we'll just go ahead and draw a line and color in the moment diagram. How about that? We're already on to the reflection questions. So the first reflection question we have is, how does the elemental transformation matrix differ for truss and frame elements? Then, how are distributed loads applied in FEA? Next we have, how are axial shear and moment diagrams created? I guess we just covered that about a minute ago. And we have one more question, and that is, how could a hinge be introduced at node 2? And more specifically, we'll say, assume we want to keep the angle that corresponds to element 3. So after the solution runs, we hope that the output angle corresponds to what node 2's angle would be on element 3. All right, and that concludes this video for an example problem using frame elements.